Yeah. So, with that, right, talking about my travel plans here, thanks for coming back. It's almost the holiday, so I do appreciate you taking the time to be here. We're going to talk today about real turbines and pumps, right? So how do we go from these kind of idealized versions of turbines and pumps that we've been talking about, where the specific entropy doesn't change, to get back to something that you'd see in the real world, something that's not ideal, right? So to do that, just a couple review slides here, right? So we'll be talking again about entropy, right? And particularly, we'll have to remember how to fix specific entropy. The examples we're going to do today are for water-based devices, so a steam turbine and a liquid pump. But you could do a similar thing on an air compressor as well. Oh, it looks like I'm not. There we go. Right. So the other thing that we've been talking about, right? So far, when we've been talking about turbines and pumps, we've looked at ideal turbines and pumps, right? At least in the last couple of days. And that ideal, another way we say that in thermodynamics is we say that it's reversible, right? It's that idea that if you let a pendulum go, the reversible pendulum will come all the way back up to the same height that you let it go from, whereas the real pendulum has some friction, so it's the oscillations are damping out, right? We know that these reversible processes don't exist. So today we're going to start to talk about how do we compare a real process to an ideal process, right? How do we grade the efficiency of a real turbine or a real pump, right? So if we did a second law analysis on ideal and real turbines and pumps, some of those assumptions are the same, right? So in this class, all of the analyses we'll be doing will be at steady state. The nice thing about turbines and pumps is that typically we don't model heat transfer from these components, right? Remember, when we talk about the first law, we say that these components, the power term is much bigger than the heat transfer rate term. So we can generally assume that they're adiabatic, or at least close enough to not losing heat, right? So when we do this, right, if it's a real turbine, then we can't cancel out this entropy generation rate term. We know that this has to be a non-zero value that's positive, right? Now, oftentimes, but not always, turbines and pumps would be one inlet and one outlet. So if we make that assumption, we'll know from conservation of mass that if these things are one inlet and one outlet, then the mass flow rates are the same. So then that would go away. There'd only be one mass flow rate. So it would be sigma dot times m dot multiplied by, in brackets, S out minus S in. So in a reversible or an ideal turbine and pump, we know that sigma dot would go to zero, right? So in a reversible or ideal turbine and pump, the change in the specific entropy is zero. Now, we talked about this when we looked at that coal power plant example. Remember when we went kind of all the way around the horn there? We looked at a full cycle that included turbines and pumps, and the way that we fixed the outlet of the turbine, and I think the inlet of the pump, was we did this second law analysis and said, oh, the specific entropy doesn't change, right? Now, that's true in the ideal case, because in the ideal case, this sigma dot term goes to zero. But in the real or irreversible turbine or pump, then we know that the delta S does change, right? So there is a value of delta S, and that the outlet specific entropy has to be larger than the inlet specific entropy, right? And we talked about this idea when we first started to draw TS diagrams, right? So we have this ideal case, right? The ideal turbine, the entropy stays the same from state 1 to, remember, we called that state 2S, right? That's the isentropic outlet. Isentropic, right? It's isen is kind of like iso, it means stays the same. And then tropic here is kind of talking about entropy, right? So the entropy stays the same. That's what the word isentropic means. But the real turbine, if we draw it on this TS diagram, this is why we like these TS diagrams, because these lines are going to go down and to the right. The pump is similar, where the ideal pump goes vertically upwards, right? And then the real pump goes up and to the right, because in both of these processes, because they're real, the specific entropy increases. So when we talk about an ideal turbine, right? The nice thing about this is that we don't necessarily need a lot of information to fix the outlet state, right? Normally, to fix a state, we need two independent intensive properties. But the nice thing is, if we know it's an ideal turbine, we know one of those properties is that S2S, the specific entropy at the outlet of the isentropic or ideal turbine, is the same as S1. So that's a vertical line. So we only need one other piece of information if we're talking about the ideal turbine, right? So we get this bonus piece of information that S1 is equal to S2S, right? So maybe we know the pressure difference across the turbine. That's often the case because we're dropping the pressure as the steam is expanding over those turbine blades, the pressure decreases. So if we know the pressure and we know it's isentropic, then we can fix the state, because then we have two independent intensive properties. For ideal pumps, we have to remember, right, this is one of those things, right, that on the exam, people will often forget, because, you know, in so many ways, thermodynamics is kind of like this choose your own adventure, right? But you got to pick the right adventure if you want to get to the right answer. Right? We have all these different equations to find things like delta H, but for an ideal pump, we have a special relationship, right? For an ideal pump, we say that the change in the specific entropy is approximately equal to the specific volume, doesn't matter which state, because we'll assume they're about the same, multiplied by the change in pressure. Now, when I originally introduced this equation to you, right, I said that this works for an ideal pump. And what I said was, oh, we'll just say for now, because we don't know what ideal means, we'll say that the temperature at the inlet and the outlet of the pump is approximately equal to 0, right? And now that we know how to use equations to find this change in entropy, we can see that that's the case, right? So here, because I'm subcooled liquid at both ends, right? Or maybe it's saturated liquid at the inlet, but that's okay. There's still no vapor, nothing compressible in the system. Then I can model delta S as Cp times the natural log of T2 over T1. Or in this case, I guess it would be T4S over T3 if I was trying to find S4S minus S3. But if you take the natural log of 1, you'll find that the answer is 0, right? So to get a change of entropy of 0 across this pump, what we're essentially saying is that there is no temperature difference across that pump. Now, I've had some people ask questions when I draw this out that here, this is a vertical line up, right? And the temperature here is changed, like temperature is the vertical axis, right? So this graph makes it look like the temperature is changing. Part of that is because ideal pumps don't exist, right? Part of it is also because this is not to scale. So if this was to scale, the slope of this line here would be much more pronounced. So this line would be much shorter than it's drawn here. But I like to draw it large just so we can see it. So there is a very minimal temperature change across a pump, right? Like, I don't know if you've ever run an aquarium, or what do they call it? Like a fish tank or something, right? But you have little pumps in there, and it's not like you're boiling the water as it goes. Or if it is, you got something wrong with your pump, right? So the temperature here generally doesn't change, right? And if that's happened, then delta S is approximately 0, right? So that's how we do ideal pumps and ideal turbines, right? So now the question's going to be, how do we find the real state, right? How do we go from these idealized versions of things like turbines and pumps to what's actually going on in real life? And to do that, we'll define something called isentropic efficiency. Right now, remember, I'm kind of a stickler for the word efficiency for two reasons. One, because I think colloquially it kind of means goodness, right? But in thermodynamics, it has a very specific meaning, or rather it has multiple specific meanings, right? Because we talked before about thermal efficiency when we're looking at a whole heat engine, how much of that heat that we put in got turned into power, right? Which is what we're trying to do. Isentropic efficiency is going to only really make sense when we talk about turbines and pumps, because those are the components where when something is isentropic, it's also ideal. So you only really talk about isentropic efficiency for turbines, for pumps, and for compressors. Compressors are essentially the same thing as pumps, but we talk about pumps when we're talking about moving liquid or increasing the pressure of a liquid. And we talk about a compressor when we're talking about increasing the pressure of a gas. So we talked about this curve here, right? So the ideal turbine and the ideal pump are vertical lines, right? The turbine goes down from high pressure to low pressure. The pump goes up from low pressure to high pressure. We know that the real turbine has some increase in entropy, right? Where the outlet state, the entropy is higher than the inlet state, right? So here I can draw two of these things. And if I could fix state 1, state 2s, remember that's where the entropy stays the same, and I knew something about state 2, then I could compare the power produced by this real turbine with the power produced by the ideal turbine, right? And I could do the same thing with the pump, right? Again, here the temperature difference is very exaggerated here as I'm moving up and to the right. But I just want to show you that, again, the entropy is increasing here, right? So then we have this real device, and we can compare the real device to the ideal device, right? We know that the real device is never going to perform as well as the ideal device does, right? Otherwise, the ideal device wouldn't be ideal if the real device was better, right? So what we're going to do here is we're going to define this efficiency to compare the real and the ideal devices or components, right? And we're going to call that an isentropic efficiency. So we know that the word isentropic, it means that the entropy of the system doesn't change, right? Or the specific entropy doesn't change. That's why we have vertical lines down for the turbine and up for the pump. This is kind of another fancy word for ideal. I would say that they're not direct, synonyms? What's the word where you have to, I'm in engineering, not in English. I think that's, two words mean the same thing, right? It's not exactly the same as that because isentropic really specifically means that the change in entropy is 0. But we only ever talk about isentropic processes when it also means that it's ideal, right? So that's why we only talk about isentropic efficiencies for turbines, pumps, and compressors, right? So it's the process, if it's isentropic, it will be ideal if the process is also at steady state, has one inlet and one outlet, and is adiabatic. Because then if I do my second law analysis, like we've seen, then if I do that and delta S is equal to 0, then sigma dot must be 0, right? So when we talk about isentropic efficiencies, either for turbines or pumps, what we're going to be comparing here, remember, the purpose of both of these, or the characteristic property that we're looking for both of these different types of devices, for turbines and pumps and compressors too, is the power, right? So the turbine generates power. So we'll look at, what's the power generation of the turbine versus the ideal turbine? A pump consumes power. So we'll compare the power consumed by the real pump and the power consumed by the ideal pump. Right? In both of these cases, this is how we're going to try to go about defining what these terms mean. The efficiency can only be 100% as a maximum, right? It's not like, like interviewing an athlete at the end and they gave 110% or whatever. Efficiencies, you have the wrong denominator if you get more than 100% efficiency, or you messed up somewhere else in the math, right? Because the thing you're dividing by is the best possible thing you can have. Right? So the ideal turbine produces the most possible power you could get as you're moving between those two pressures, right? And the ideal pump consumes the least amount of power that's possible to increase the water pressure like we're doing, right? So here, a first line law analysis of a turbine. Hopefully this isn't too surprising, right? We're at steady state. We'll typically neglect changes in potential and kinetic energy. We'll assume that it's well insulated or adiabatic, basically that the heat transfer term is much smaller than the power term. We will often assume that they're one inlet and one outlet. So the first law analysis from the turbine tells us that the power produced by that turbine is m dot times h in minus h out, right? And remember, this is kind of what we expect, that at least the enthalpy term in a turbine will come out as high ho, because we're trying to find work. And with a turbine, we expect this to be positive because the turbine is producing power. So if I was going through the ideal turbine, the inlet state would be H1, and the outlet state would be that H2S. That's the specific enthalpy if the entropy didn't change. The specific entropy didn't change, right? So this state 2S, it's the imaginary state of what that ideal turbine would look like if it could exist, right? That's that vertical line down, right? But the real turbine is m dot times H1 minus H2. The difference here, it's the same equation, right? It's still m dot times H in minus H out. The difference is the outlet of the ideal turbine is this state 2S, and the outlet of the real turbine is state 2. So now my question is, which one of these things is bigger? Right? Because the purpose of a turbine is to produce power. That's the turbine's job. So if we were in a room, I'd ask for a show of hands. So instead, I'll probably just give you the answer, right? But the ideal turbine, if you're going through the same two different pressures, is going to produce more power, right? Because in the real turbine, right, there's friction in the bearings, for example, right? Because you're making this spinning shaft, and that shaft is spinning on bearings. So some of that power that, if there was no friction, would go into sort of the torque on that shaft. Some of that power gets robbed, gets consumed by the friction in the system. So the real turbine has to consume a little power just to work, right? Whereas the ideal turbine doesn't. So which one is bigger? It's the ideal turbine, right? Because the ideal turbine doesn't have to have friction that's robbing its power, right? So because the real turbine also has to deal with friction, so it produces a little bit less, right? But another way you can think about it, right, is that the turbine is producing power. That's its job, right? And the power associated with the turbine is a benefit, right? That's what we're trying to do in a heat engine, is produce power. The ideal process always does better than the real process. So a turbine's trying to produce power, so an ideal turbine must produce more power than a real turbine because it does it better, right? That's why it's ideal. So a turbine efficiency is going to be power divided by power, right? One of these powers is going to be the real turbine, and one of them is going to be the ideal turbine. Now we know that the efficiency of the turbine has to be less than 100%. It just has to be, right? Because otherwise it's not an efficiency. So we need to put the bigger number on the bottom, right? And we know that the turbine, the ideal turbine, produces more power because it's ideal, right? The ideal power is bigger than the real power, so it's the ideal power that goes on the bottom. So if we're talking about the isentropic efficiency of a turbine, we take the real power of the turbine divided by the ideal power. So after I've done my first law, right, this is just going to be m dot times h in minus h out. So this is m dot times h1 minus h2 divided by m dot times h1 minus h2s. But the thing about the real turbine and the ideal turbine, it's the same mass flow that's going through these things, right? The ideal turbine actually doesn't even exist, right? But we're talking about it only makes sense to talk about if it has the same mass flow rate. So this is really going to boil down to H1 minus H2 divided by H1 minus H2S. Right? But we'll see that as we go through the example. We can do the same thing for the pump. Right? We're going to have the same assumptions that we had for the turbine. Right? We're going to get the same equation that the power of the pump is m dot times H in minus H out. But the states are different here, right? I've labeled them just as 1 and 2s, right? I know on the previous diagram, it was 3 and 4s. But here, 1 is just the inlet. 2s is the ideal outlet of this pump. And state 2 is the real outlet of the pump. Now, here's where it gets a little bit tricky, right? Because again, we want to ask ourselves, which one of these two numbers is bigger? Right? With the turbine, it was the ideal turbine that produced more power because the power from the turbine was a benefit. The power we're talking about for the pump is a cost, right? So, right, because we got to plug this pump into the wall, right? And we're actually kind of, in a power plant, we're using the power produced by the turbine. The power plant is the first consumer of the power from the power plant. So the pump is actually being driven by the power created by the turbine, right? So this is a cost, right? So which one has the higher power requirement for a pump? It's not the ideal turbine, or it's not the ideal pump, it's the real pump. Because the real pump, we got to put in enough power to spin the shaft enough that we increase the pressure. But we also got to put in just a little more power to overcome the friction in the bearings, right? So it's the real pump here that consumes more power, and that's because the power here is a cost and not a benefit. You don't really have to memorize these things because they're on the equation sheet, but I do think it's nice to understand why they're different, and it also, my kids, they're a little old for Dora now, although my 3-year-old kind of, but I think my wife got tired of having Dora on in the background. So my 3-year-old doesn't watch Dora. She watches other shows that are annoyingly repetitive. But one of the things that Dora always says, right, is, stop and think, right? So when you're using an isentropic efficiency, it's nice to kind of stop and think about which power goes on the top and which one goes on the bottom. Because if you're like me, sometimes on an exam, you'll go a little bit too quickly, and then when you get it back, you're like, oh, I can't believe I did that thing, right? I can't believe that I inverted this and then I got the wrong answer, right? So for the pump, it's the real power that's bigger than the ideal power. So for the pump efficiency, it's ideal power divided by real power, right? So it's the same concept. It's still the smallest one divided by the biggest one, but because the pump power is a cost, then the pump power goes on the bottom in the real case here because the real power or the real pump requires a higher cost to run than the ideal pump. Okay, so how do I fix the states? Right? So there's really two ways I can ask isentropic efficiency questions, right? Is one, I can give you enough information for this turbine to fix state 2s and state 2 and state 1. And then you can find the power produced by the real turbine and the power produced by the ideal turbine, and you can tell me the isentropic efficiency, right? The other thing I can do is I can give you only enough information to find, say, 4s, and then I can tell you the isentropic efficiency, and you can use the isentropic efficiency to fix state 4. So we're going to go through and do both of these types of examples here today. I'll just move this over to the other screen. Close that. And these are the two kinds of questions. It's not like we'll only ask this kind of question for turbines and we'll only ask this kind of question for pumps. But there's basically, with isentropic efficiency, there's two ways that I can set up this problem, right? And in this problem, you can see here, I've got two independent intensive properties here at state 1 and two independent intensive properties here at state 2. I only have one property at state 2s, but I know that that here S2, I think it doesn't really like that, right? S2s is going to be S1, right? But I'll just walk you through how to do this problem. And there's two ways to ask this problem. So hopefully we'll be able to get through both of these examples. If I don't, you can check them both out on the long version of this video that's up. But also, I mean, I would just always recommend watching the thermal shorts because they sort of cover, at least at a high level, all these same problems that we're doing. So there's a playlist for that. I think you can get to it through my courses, but it's also just on my YouTube channel. So we know that a turbine has the following parameters. Find the isentropic efficiency of a turbine, right? So here, we know we want the isentropic efficiency of the turbine, right? This turbine efficiency, I know is going to be power divided by power. So now I'm going to think a little bit about a turbine, right? It's funny, I hope that you end up learning more than this, but I had a friend in undergrad, and what he said he learned in thermo was that, turbines are, whatever, these four-sided shapes where it gets bigger towards the end, and compressors are ones where it gets smaller towards the end. So hopefully you learn more than just how to draw something like this, right? Right, so here we have this control volume, right? And this turbine, the purpose of the turbine is to produce power. Because this is an energy benefit, the ideal turbine goes on the bottom and the real turbine goes on the top, right? I've drawn my control volume. Here my turbine has one inlet and one outlet, so I can say dm by dt is equal to the sum of the mass flow rates in minus the sum of the mass flow rates out. My system is at steady state. I have one inlet and one outlet. That tells me that m dot in is equal to m dot out. So there's really only one mass flow rate in the problem, right? Hopefully that part's not surprising, but it's good to review this stuff because the second exam is coming up and the second exam is going to be about open systems. So we want to know how to deal with these open systems. Right here, maybe I'll zoom in here in case if you're watching on a smaller screen, maybe that's useful. Right, next we'll do a first law analysis here. So dE by dt is equal to Q dot minus W dot plus the sum of M dot in, H in plus V in squared over 2. It's metric, I think. Yep, so I don't put the GCs. Plus GZ in minus the sum of M dot out, H out plus V out squared over 2 plus GZ out. Here, this is going to be at steady state. It's going to be adiabatic. One inlet, one outlet, and I can neglect changes in kinetic and potential energy. So again, hopefully this isn't too surprising since we just talked about it, that the power from my turbine is going to be m dot times H in minus H out. So I can use this back up in this equation for both the real and ideal turbine. So now I'm going to just move over here a little bit, right? So my real turbine is going to be m dot times the real inlet is state 1. It's never the inlet that changes. It's always the outlet that's different if you're talking about real and ideal processes. So this is H in minus H out. H out of the real turbine is state 2. Here we're going to divide by m dot times H in is still the same, H1, but the outlet is H2s. Now, the mass flow rate with the real and ideal turbines are the same, right? So here I know that my thermal efficiency equation for the turbine is going to be H1 minus H2 divided by H1 minus H2s. This is great because I have a symbolic solution, right? And you can see, just like with most of the symbolic solutions we find, this didn't take a ton of time to do, right? Just to get to this equation. But unfortunately, I don't think we know H1, H2, or H2S, right? And we're trying to find this, so we don't have that either. So here, I'm just gonna, we can go back and find the numbers, but I'll walk you through the process of how I would find this, okay? So the pressure here I'm gonna draw my TS diagram. Maybe I'll, let me copy this as an image down here. No, I think it likes it better if I draw on it when it's an image. So why don't I do this? Oops. I know this is the super exciting part of the lecture. Okay, so I'm going to draw now my TS diagram. Just kind of small over here. I'm going to assume that going into the turbine, we're up here in the superheated vapor region, right? I can double check that when I fix that state, but I think that this should be superheated vapor. It can't be saturated vapor, or if it is, I'm in trouble, because here, 10 bar and 600 degrees, it wouldn't be good, right? Because I don't have, so I'm going to assume that this is table A4. So remember, 10 bar and 600 degrees. I think I've snipped some stuff out down here. So 10 bar and 600 degrees. So I'm going to take this value. So this is my H1, right? So now we know this value here, right? I would also take S1 from there as well. Now here, we're coming out at some lower, it looks like a temperature we have, right? 45 degrees. And this is going to be, oh, that's the real outlet, right? So it's going to be down here, right? So this is going to be HG at 45 degrees and SG at 45 degrees. Oops. So the good news is here now, pretty simply, right, because I have two independent intensive properties, I can find H1 and H2, but I don't yet know H2S. Here, if I draw this a little bit better, here's my high pressure. The other thing I know is a temperature, right? Here, I know that this is state 2. State 1 has to be over here, right? Because it's got to be up and to the left. So if I do a vertical line down, state 2S has to be here, right? So because this is saturated vapor and these are the same temperatures, I know that this one has to be under the vapor dome. So here I'm going to use table A2, right? So what do I know? I know that S of 2S is equal to S1. But I also know that S of 2S is going to be equal to SF plus X of 2S times SG minus SF. Right? If I wanted to double check, right? So here from my graph, I think that this is true. So here I could check this. Is S1 in between? So is it lower than SG at 45 degrees and higher than SF at 45 degrees? I believe that it will be, and it'll be pretty close to SG. So when I look at this thing, I know S2S because it's equal to S1. I know SF and SG, those things I all evaluate at 45 degrees from table A2. So what I'm going to use this equation for is to find X2S. So here I'm going to say X2S is equal to, I'm going to say S, I'll say 2S just so it's less confusing, but I'll remind myself here that S2S is S1 minus SF divided by SG minus SF, right? So in this equation, I know all these S's, so that's going to give me X2S. Now, you might have said, maybe I could have done this before, because actually, who cares about the S's? Because in the equation that I have for the thermal efficiency, it's the H that I want, right? It's actually H2S. So maybe I should have written this one down first, because I don't know what this is, but this is going to be HF plus X2S, HG minus HF, or HFG if you like. Here, we know only the H values, but we don't know H2S because it's the specific entropies that are the same, right? Not the specific enthalpies. And we didn't know X of 2S. So if I started here, then I would have one equation with two unknowns. And then I'd have to remember, oh, this is the isentropic outlet, which means that the specific entropy at 2S is the same as S1. So maybe I can use that equation to find this extra information so I know that X of 2S is equal to something based on my understanding of S1, right? So then once I know this, then I can find H2S and I can put all those values into my isentropic efficiency equation. If you wanted to actually do the math, again, you can check out something like the thermal short or my notes that are online. But the turbine efficiency here, right? So here are the values if you want to fix them. Right here we can see that, right, S2S is equal to S1. We know that it's that S2S is lower than SG, right? Because this one is at quality, so this is SG. So then, you know, we can kind of figure this out, right? But that's the process that we use, and I walk through that on the slides with the numbers. If you look at the thermal short, or if you look at my notes, or if you look at the sort of long version of this example that's in the, I think it's called like Thermodynamic Lecture Series or something, the playlist. So that's good. Once we do that, then up here, all of these H's now become known because we fixed the state. And then, you know, now we know the thermal efficiency of the turbine, right? Which, and now I moved off the sheet and I forgot what it was. But, you know, typically these efficiencies are relatively high. It's not like when we talk about thermal efficiencies, this one was 96.2%. So typically turbine and pump efficiencies tend to be fairly high. Whereas when you look at like a thermal efficiency of a power plant, you know, it'll be in the 50s or the 60s or something. And, you know, and you look at it and you might think, oh, that's not, doesn't feel like that's so good. So this is one way. This way, this kind of problem, this kind of isentropic efficiency problem was we fixed. So here we found state 1, state 2S, and state 2. And we used all of this to find the efficiency. But on an exam, you know, there's different permutations of, you know, allowing you to demonstrate the same kind of information. So I can also maybe give you state 1 and state 2S. And then you can use that and the efficiency to find state 2. And that's what our second example is going to do here. So here we have a pump, right? And it has these operating parameters. And we know that the isentropic efficiency here is 90%. Knowing that, how do we fix the real outlet of the pump? Right? So the pump is just like the turbine, right? So it's at steady state, one inlet, one outlet. and adiabatic. So from all of that, we say that that m dot in is equal to m dot out. We get that from continuity or conservation of mass. And we'll also find that w dot of the pump is equal to m dot times h in minus h out. But, right, where with the turbine, we expected that power to be positive, with the pump, we expect the power to be negative, right? Because the turbine is producing power, and the pump, if I draw a schematic of the pump over here, right, with my control volume around it, the power here is going into the pump, right? So this is work in. Work in is negative, so we expect this value to be negative. The textbook will tell you that pump power is m dot times h out minus h in, which is true if you're talking about the magnitude of the pump power, but it kind of gets rid of the hip to win sign convention that we've been using throughout. So I try to keep that throughout the course. So again, we talk about a thermal efficiency, but this time of a pump. So it's still going to be power divided by power. But here, right, because this is a cost. This pump is this power is a cost. So the ideal pump, the pump without any friction in it, requires less power. So here the ideal pump goes on the top and the real pump goes on the bottom. Right? So now this is going to become, right, because I know my pump power equations, this is going to be m dot. The ideal pump, the inlet is, we're calling this state 3, and the outlet is H4S. Right? And then for the real pump, this is going to be m dot times H3 minus H4. So now it's a little different than when we were rearranging things last time, because this time it's H4 that we don't know, and we're told the isentropic efficiency of the pump. We still haven't actually fixed any of these things yet. But when I do my symbolic solution, I would like to usually have, the thing that I'm actually trying to look for in the problem isolated alone by itself on one side of the equation. So here, right, I'm going to do this thing where I, move this into the denominator. And well, first, before I do that, I guess, I'm going to say that the mass flow rates are the same, so I can cancel those out, right? But this equation here, this is the same as H3 minus H4 is equal to H3 minus H4S divided by the efficiency of the pump. I remind myself that it's actually H4 that I'm trying to find out, right? So I move that, by itself on one side of the equation, and then I move this term here with the isentropic efficiency in it to the other side of the equation, right? So I'm going to have H4 is equal to H3 minus H3 minus H4S divided by the thermal efficiency of the pump. Right, so now at least I have a symbolic solution with the thing that I'm looking for isolated on the left-hand side of my equation. The good news is I know the thermal efficiency here, or not the thermal efficiency, the isentropic efficiency of the pump. I was told that's 0.9. I don't know H3, and I don't know H4S. So what do? I can look up here. I can find H3, right? This is going to be HF at 45 degrees, right? And if I wanted S3, that would be SF at 45 degrees. So those two things I can fix, right? But the thing that I do here, right, I remember this is the thing, right? When you have an ideal pump, you got to remember your spidey sense got to start tingling a little bit, right? So this is delta H across an ideal pump is equal to the specific volume at either case, but in this case, it's going to be state 3 times delta P, right? And in this case, my delta is H3 minus H4S, right? But the pressure difference, so P4S is equal to P4. Because it doesn't make sense to compare an ideal pump that's doing a different job than the real pump. So the real pump has to increase the pressure of the water by a certain amount. The ideal pump has to do the same job, right? So P4S is going to be the same as P4. So here, right, we're going to want this specific volume at state 3 times, this is going to be P3 minus P4S, which is the same thing as P4. I'm just going to do a quick check here of my units, right? Specific volume, right? It's been a little while since we talked too much about specific volume, but this is in meters cubed per kilogram. Pressure, I remember Dr. Schertzer told me to talk about kilopascals, right? Because kilopascals is equal to kilonewtons per meter squared. And the cool thing about that is going to be, this is going to be kilonewton meters per kilogram or kilojoules per kilogram, which is good because that's the same thing that I looked up H in when I looked it up on the table. So this equation now is going to become H3 minus, we're never going to find H4S, but that's okay because here we're going to make this substitution. This is going to be V3 times P3 minus P4S divided by the pump efficiency. So now we've looked this up. V3 is going to be VF, also at 45 degrees. Right, so we know V3. Do we know P3 and P4S? So we know P4S is 10 bar. To get P3, here, I'll show you how to get P3. So here we're going to go down to this table, right? We know that the temperature here is 45 degrees, right? So here we would get this specific volume here. We remember that we actually have to divide that number by 1,000. It's not 1, it's 1 over 1,000, right? We get HF over here. And then we get P3 over here. Because the pressure, right, because we're a saturated liquid, so that means we're at the right pressure to boil if we're at 45 degrees, but we're not boiling, we're just at that right pressure. So this is the right pressure. So about 1/10 of a bar, right? Or that's 10 kilopascals. So we know this, right? And the other thing we see, right? So P3 is about 10 kilopascals, right? And P4S is, what did it say, 10 bar? So 10 bar is 1,000 kilopascals. Right, so this number here is negative. And that's what we expect, right? Because pump power should be negative because the pump is consuming power. Work is going in. So that's good, right? So here we want H4 to be bigger than H3. And this is going to be H3 minus some negative number. So that's going to give us the right answer. So from here, or at least an answer that's got the right sign, right? Because we never really know if we get the right answer, but at least we can't prove ourselves wrong, right? So here we checked our units. So we got units in the right units, right? Here we can see what we're going to see here too, right? Because the other thing we saw, so here we're going to find H4, right? So I can look at H3 minus H4, and I can look at H3 minus H4S, right? And both of these things, if I multiply them by the mass flow rate, that would give me the power. And what I've been telling you, right, which is the truth, is that the ideal pump consumes less power, right? So then we know that this delta has to be less, right? So this one is bigger, right? And we can see that because here I'm dividing by something less than 1. So this number here, this delta, right? Because this is basically going to be the delta H for the real pump when we divide it by this. So it's the delta H of the ideal pump divided by 0.9, right? So that's multiplying by like 1.11 or whatever it is, right? So here the delta is a little bit bigger, right? So here we would be satisfied that that's more or less correct, right? I could still fat finger it on my calculator. Like I've said, I'm really pretty good at that. But here I can see that the difference that I got for this real pump was just over 1 kilojoule per kilogram. Where when I calculated, right? So this was 1.11 kilojoules per kilogram difference across the real pump, but it was only 1 kilojoule per kilogram difference across the ideal pump. So it's a little bit different, right? And that real pump has to consume a little bit more power because it's got to overcome all those irreversibilities, things like friction in the system. So that was all that I had for you before the holiday weekend. I'm happy to stick around for a couple minutes if people have questions. I will also be around at 2 o'clock if you're not on vacation yet. Thanks, everyone.
Did you ever get a chance to look at those two homework problems, the 6.8 and 6.8?
Oh, sorry, I forgot to do that. I will do that today. I did change the date, which I know we had talked about before, from the 5th to the 6th, but I forgot to look at those problems. My note to myself obviously wasn't specific enough. What was the numbers? They were 6.8
and 6.82.
Okay, I will do that right when I get off the class here.
Okay.
Okay, thanks, Dan.
All right, thank you.
Yep.
Thank you, Professor. See you later today.
Yeah, no problem.
Thank you, Professor.
Have a good holiday, everyone.